Thank you all for joining us today. Today we'll be talking about our 2019-2020 SOU capstone project. The FlowJo AI team is comprised of Benjamin Mosier, Esther Wine, and myself, Miguel Velasquez. And we'll be talking to you today about the motivation behind the project, the requirements that we gathered from our conversation with the client, the architecture we put together, and we'll demo the system that we created. Lastly, we'll come back and tell you some of the testing that we implemented and give some final remarks. Now handing it off to Esther Wine.
So during the last 6 months, we've been working with our client, Josef Spidlin, the Senior Director at FlowJo. For those who don't know, FlowJo is a company that provides a program with the same name, allowing for analysis of flow cytometry data. Flow cytometry is a technique that is used to diagnose disease and discover cures in hospitals and universities around the world. FlowJo users study the immune system's response to diseases like COVID-19. These responses are complex and require training to decipher. FlowJo AI was built to help decipher these responses programmatically. So what does our client need? Our client wants a software that will be able to classify immune cells within the FlowJo application. These classifiers need to be scalable and shareable. So this is where FlowJo AI comes in. FlowJo AI makes it easy to train and deploy classifiers, and overall will reduce the time from patient visit to diagnosis, potentially saving a life. The major requirements are few, but hold a lot of detail within them. Most importantly, the software needs to be able to classify cell types, as that is the main purpose of the program. In order to do this, the software must allow users to be able to start a training job based on their input data set. After doing so, the user should then be able to create a model, which will be stored, create an endpoint, and finally be able to run inference on any of the given models in their list. One of the requirements that is an important addition is the use of real-time feedback. While running any of the number of provided services, the software will notify the user of their progress on their current task, whether that be the status or info about the training algorithm. All of this will be integrated through an easy-to-use UI in FlowJo Prime, so the user is able to quickly access any of our provided services. Now handing it off to Ben to talk about how all of this is put together.
We chose to use Amazon Web Services, or AWS, to host the FlowJo AI system, as it is the preferred cloud provider of our client FlowJo. A number of AWS services make up the core components of FlowJo AI and make up our serverless architecture. FlowJo AI uses Amazon SageMaker machine learning platform to instantiate training instances and system endpoints. Amazon Simple Storage Service, S3, is used to hold intermediary model data. AWS Lambda functions trigger system actions and are directly connected with our WebSocket API gateway. Model management and tracking is stored into the NoSQL database, DynamoDB. We use Python and the PyTorch machine learning framework to train our particular models. Docker containers serve and dynamically load our machine learning models. And the FlowJo Prime is a modern front-end application built with Electron and React Redux frameworks.
So FlowJo Prime is an application developed by FlowJo, as we said earlier, and Prime is built on top of the Electron application that allows the application to run Chromium or Chrome in a desktop application separately. And for the front end, the JavaScript framework is React using Redux for state management. And for the back end, it's a C++ compute engine that does all the heavy lifting.
When the user starts the software, they are automatically connected to our WebSocket. The WebSocket takes in a request from the user, for example, the Start Training Job button in the user interface, which we will see later. When that is clicked, it sends a request to the WebSocket. The WebSocket then routes the client's request to the appropriate Lambda. Unlike a REST API, which only allows client to back-end communication, a WebSocket also allows for communication from the back-end to the connected clients. This allows for the client to receive information about the models and training from the DynamoDB, which Ben will be able to explain more on.
In order to have a stateless front-end application, we chose AWS's DynamoDB. DynamoDB is a NoSQL, low-latency, serverless database that integrates nicely with the AWS ecosystem. We set up our tables to stream all updates to our clients in real time, giving the user a second-to-second update on FlowJo AI's progress.
Okay, so now time for a demo. So what we have now here is FlowJo AI. FlowJo AI is integrated into FlowJo Prime. So FlowJo Prime is the application that you see here, and these are some data files that you see here of patient data. And we've created a platform inside of FlowJo Prime for our FlowJo AI service here. So once we come in here, we see that we have on the left-hand side, obviously FlowJo AI, but on the right-hand side, connected. That means that we are connected to this WebSocket server. So as Ezra alluded to earlier, we will launch a training job, which we've launched a few before. And as soon as we do that, we should see on the right-hand side a new model that is now being created. So on the left-hand side, we'll see each of the steps that a user must go through in order to create and deploy a training job and then a model that they can predict against. So as you see, each of these little steps has the icon to the service that is mapped in AWS. And as Esther mentioned earlier as well, is that every single one of these requests that we will click here, go to the Lambda back down. And so once these are done, the compute instances are being created in which we will run FlowJo AI, we'll come back and we'll see the next step. Okay, so once our instances are created, we download the Docker container automatically and the input training data set. And at this point, what we'll see happen in the next few moments is SageMaker put together all the different ingredients that it needs in order to start a training job. So this goes from setting up the Docker to putting the data inside the Docker container, putting the container into a compute instance that we've already created, and then after that, starting to create all of the data frames that it needs to put the data into in order to then read them into our PyTorch trainer. So what we'll see on our right-hand side in a few seconds, we will see the update of each one of the epochs. And just to sort of give a quick understanding of what's an epoch. An epoch in machine learning is used to refer to every time that you will run through putting your whole data set through a model. And the way that the machine learning model works here is that we have random weights that are initialized, and what the model tries to do is tries to learn patterns by changing these weights at each epoch. So what we want to do here is run through, allow the users to set their amount of epochs that they want to put their data to the model, and ideally with each epoch you will see a higher accuracy and a lower loss, which means that the training labels that you gave it, which are the ground truth, compared to the labels that the model predicted, will be minimized. So we should see that start in a few seconds. Okay, so as we're seeing now, each one of the epochs that our model will run through will now be updated live here in front of us. And one of the things that we see here is we have 100% accuracy on this model immediately, and that is something we expect because the data set given to us by the scientists at FlowJo we know is highly differentiable, and that is something we expect at 100%. So once these 10 epochs are done, we'll see here that we first went through some loss, went down, and then eventually went back up, but we will take the lowest loss as the best loss for the model. So once this model has completed training, and generally it takes much longer time with much larger data sets and real data sets, we will go ahead and grab all the model, upload it to an S3 bucket, and then the model will be ready for training. So what we'll do now is we come here, and first thing we need to do is, as a user, one of the use cases was that they have to look at the accuracy and see whether or not they want to launch this, or whether or not they want to launch it at all. So given it's 100% accuracy, yeah, we want to launch this. So we click prepare model for deployment. It gets packaged up and ready and gets created such that it can be deployed. So once it's ready for deployment, we will ask for SageMaker to deploy this model. And so what will happen now is that SageMaker will take our training script, our predict script. It will take our model. It will take any configuration that we might have set up for it, and it will create an endpoint that it's a URL that we can hit through AWS using our Lambda service to predict. So when this is done, we'll be able to predict in real time. Okay, so our predict endpoint is now ready. And so we can grab this predict endpoint and we can run prediction against it. But first we'll do an update. So we're gonna call this, this is gonna be a CD4 classifier. Okay, so we're gonna go ahead and save this. Once this is saved, it gets saved to our database, and now we can go ahead and run predict. So what predict runs is that we'll be able to download a file, which I downloaded ahead of time here. This is prediction and classes. And what we'll do here is that we'll go ahead and parse the file. And what the front end will do is it takes each of the classes, enumerates them, and counts them up. And then it gives us an overview of what cell types were predicted from the data set that we sent over, which is this data set here. And so what this will allow scientists to do is they will allow them to classify these cells and integrate them back into FlowJo as populations, or gates as we call them in the scientific world. So that's the demo for FlowJo AI in FlowJo Prime. So now just a quick recap over what we did. So we started a training job. That training job went over into our backend. It started all the SageMaker services that we needed. It then went ahead and completed. We grabbed that successful training job with close to 100% accuracy. We created a model for it so that it could be deployed. We then deployed that model so that we can get an endpoint, which we can call over a WebSocket connection. And lastly, we just went ahead and ran predict. So we told it, here's a data file in S3, go ahead and grab that file, predict. It was extremely fast. We downloaded that classes, that CSV right now to the desktop, and we read it back into the application, which is something will be integrated directly into FlowJo in the future. And we saw that we predicted these classes. And during the whole time, we saw our update model of lambdas being called from inside of the services, which updated the database. And lastly, we saw that the model stream lambda, which updates all the clients, was working because we saw everything real life. And so now I'll switch it back over to Esther Wine.
Okay, our tests basically correlate to the major requirements. Obviously, being able to access the plugin and successfully connect to the WebSocket is most important, which we showed we could. We needed to make sure we could select data to test on and be able to train on said data, deploy a model, be able to select our test data, and run an inference on the generated model, receiving a prediction in return. It was also important that the user could see a report on their models, as we saw earlier with the accuracy, loss, and status of said models. One thing that we did not get around to, but would like to, is to implement a way to remove models from the list. Currently, we can only do it through AWS and not through the UI, so that would be a helpful addition for the user. Now handing it off to Ben to cover our division of labor.
We divided our labor with myself, Ben, leading infrastructure and PyTorch machine learning. Ezra headed development with our Terraform and client server API. Miguel was in charge of our client and cloud architecture.
So to sum it up, today we talked about the motivation behind FlowJo AI and the impact it has for scientists around the world. We showed how FlowJo AI makes model deployment, machine learning specifically, simpler and easy to use for scientists. Lastly, we talked over the system architecture a bit, what the different parts we chose and why we chose them. And then we showed a demo as to how the user would ideally be using FlowJo AI inside of FlowJo Prime. As the last remark, I'd like to say thank you, obviously, to my team, Ms. Esther Wine and Benjamin Mose here, as well as our advisor, Professor Suarez. It was really helpful and really a great time to work with you guys. Appreciate it so much.